isotope is a variant of an element that has similar chemical properties but different atomic weight. That is, it has the same number of protons but different number of neutrons. The study of isotopes can have very important applications, as we are about to find out here in the cosmochemistry lab of the Institut de Physique du Globe de Paris. And joining me now is Frederic Moynier, who heads this lab. Thank you for your time. Before we start with your research project, can you give us an overview of this lab?
So here in this lab, we are studying isotopes. So we use this abundance of isotopes of various elements to understand the processes that have formed planets like the Earth or the Moon. So for example, here in this room, we are in what we call a chemistry clean laboratory. It's where we're going to study samples like, for example, here, samples collected by Apollo mission. This is an Apollo 11 mission sample. It's a piece of basalt inside this tube. And by looking here at this sample in this lab, we're going to crush the sample, we're going to dissolve the sample to extract elements, for example, potassium or iron, in very clean environments, to then take the sample to a different laboratory, which is what we call a mass spectrometer, in which we're going to analyze the very precise abundance of each isotopes of all these elements.
How does the study of isotopes help in determining the formation processes of the terrestrial planets in our solar system?
Isotopic abundance can be seen as a fingerprint of all the processes that could affect an element. So for example, when we study the Moon, after the first Apollo missions, we realized that the big difference between a moon rock and a terrestrial rock is the depletion in the most volatile elements. This is obvious when you look at the Moon. You see there is no water on the Moon or no oceans compared to the Earth. But if you take a piece of basalt of the Moon, we will see there is 10 times less sodium or potassium compared to a terrestrial sample. When this was observed, we were not able at that time to look at the isotope abundance of this potassium or zinc, or etc. But at looking at the isotopic composition, we can track back of what happened to the element. And so this way we can get the history of the element and history of the processes that has affected the planet. And by studying this isotope, to take the example of the Moon, we can tell that all these elements were there at the beginning as the same abundance as the Earth, but these elements were lost by a big evaporation event after the Moon was formed.
Can you tell us about the study of the samples that you recently received, the lunar samples, as well as those from the Ryugu mission?
So for the lunar samples, we recently received a sample from a Chinese mission called Chang'e 5. Chang'e 5 is a sample return mission that happened a few years ago and that collected samples from the near side of the Moon, but at the top north of this near side, which is a very remote area compared to all the previous missions, which were Apollo missions and Luna missions from Russia. So these samples were first geographically very different from Apollo missions. So it was interesting because all the science I have been, and most scientists have been doing on the Moon, was based on Apollo samples, coming from a very localized area on the Moon. Now we have a sample coming from another part of the Moon. So it's a good way to test whether whatever we could say about the Moon can be generally applied to the whole Moon. The other big difference between this sample from Chang'e 5 with Apollo is that it's much younger. The youngest sample collected by Apollo missions were about 3 billion years old. So samples from the Moon are above 4 billion years old to about 3 billion years old based on Apollo samples. The Chang'e 5 rocks that has been returned to Earth are about 2 billion years old. So they are 1 billion years younger than the youngest Apollo samples. It means that it has been sampled, because it's a lava, it's a melting of the mantle under the crust, a sample of a part of the Moon that is different from the Apollo samples. And so altogether, this makes this sample quite unique in our collection. And my interest is about this isotopic abundance of volatile metals like potassium, like zinc, and this will be, using this sample, I will be able in the next months to test whether what we see with Apollo can be actually generalized to the whole Moon. Ryugu was a sample from this Ryugu asteroid, which again formed very early in the solar system. Now it's formed within 1 million years after the formation of the Sun. And what we did, I was part of the initial chemical analysis team. So we realized the first analysis of the composition of this material. We realized that the composition, the abundance now, not the isotopes, the concentration of all the elements is very similar to the concentration of the sun that we can measure looking at the surface of the sun. And so this means that because the sun represents 99% of the mass of the solar system, so this is the composition of the solar system, but now we have a rock that has the composition of the sun. Right. So this was the first result. And then what we did in the lab here, we analyzed again our isotopes of these volatile metals, potassium, zinc, rubidium. We were in charge of doing these elements. And what we discovered is that the composition of these elements, of volatile metals, is a bit different from the Earth. And what it means that only a small fraction of the volatile that you find from the Earth is coming from materials like Ryugu, which we believe formed in the outer solar system. So one of the big conclusions based on Ryugu is that the volatile elements that you find in the Earth, I'm talking about the metals, but it's probably also true for more volatile elements like water, only a small fraction, maybe a few percent, are coming from the outer solar system.
Interestingly, the study of isotopes also has some very important medical applications. You are heading a project called Diagnose Alzheimer's Disease with Isotopes. Can you elaborate on it, please?
So, using the same method that we have developed to study the moon, so our isotope abundance of these metals like zinc, like copper, like iron, we realized that we can use the same method to look at how elements behave in a human body. The mechanism, the physical mechanism that explains the variations of the isotope abundance is the same physical law that will control this abundance in a body compared to the moon. And so because we were among the first ones to develop these methods, we were the only laboratory able to analyze very precisely the abundance of these isotopes. And we focalized our study on this European-funded project to study Alzheimer's disease. Alzheimer's disease, one of the consequences of Alzheimer's disease is the abundance in the brain of polypeptides, like proteins, rich in metals. So you enrich your brain in metals like zinc, like copper, like iron. And this abundance, overabundance of metals in the brain affects the whole behavior of your elements in the body. And looking with our isotopes, we were finding tracers that can demonstrate that you form these proteins in your brain, and the general idea is to use this approach as an early diagnosis of the disease.